I'll begin with a word of prayer. Dearly Father, we thank you for this day. I thank you for these students, and I just ask you to guide our work today, Lord. In your name I pray. Amen. Okay, so last time I introduced in my view, three competing definitions for the complex integral. And so let me just discuss those a little bit further. So the one definition, which was my definition 2, right, was that to integrate over some curve C, f of z dz. What did I say? It was going to be something like the limit as n goes to infinity of the sum I equals 1 to n of f of, say, zi. And, well, I think you could really put like zi star there. I'll just leave it zi, but z I minus zi minus 1, I guess, like that. And here, what we're talking about is this curve. It's a curve with a starting and an ending point. I'm labeling those z naught. I'm labeling the ending point zn, right? And then in between, we've got, z1, z2, z3, etc. Yeah. And so, for this to be, and that's the curve C. It's got an orientation, right? So for this to be the definition, I mean, if you think about it, there's something very satisfying about this definition. And can you tell me what it is? I mean, what does it look like? If I change the z's to x's, what would it be? I'm looking for my coffee, which I didn't bring, if you're wondering. Yeah, right. Yeah, well, telescoping series, I mean, kind of. I mean, isn't that just the change in z? Like these are little, like you could think of this as being delta zi or something, right? This is a pretty close analog to the Riemann sum, isn't it? I mean, if we just replace, if instead of having zi we had like, zi star or something, and we could do that without changing anything here. Where zi, this is like z1 star is something in here, z2 star would be something in there, sample points from each. Well, that's not quite right because I can't quite do that though because, well, I guess I could, but then the purple values I just wrote wouldn't actually be on the curve, which is kind of awkward. It's not quite what I want. So I think that's why we have to write without the star, logically. But anyway, my point is that this is sort of just a natural analog to the Riemann sum, yeah? Now, if this curve is smooth, or at least once continuously differentiable, right? And let's suppose it's, what do I mean by that? I mean that we can parameterize, suppose that there exists gamma going from, say, t naught to t1 to the curve C, where gamma of t naught is equal to, z naught, and gamma of t1 is equal to, well, in my current notation, zn, but I probably should come up with another name for that. Maybe we should say that let's say this curve goes from point P1 to point P2, yeah? So I'm saying P2 is Zn, and our partition is set up so that P1 is Z naught for all partitions of the curve, right? So yeah, gamma of T naught should be P1, gamma of T1 should be P2. My choices of labeling is suboptimal, right? Sorry. But it is what it is. Now, if that parameterization of the curve is smooth, right? Suppose that this is a smooth, and let's include in my meaning of that gamma prime of t is not equal to 0. So I'm saying, suppose that the derivative is non-zero along the whole curve, yeah. Then what we can do, if we look at each if we look at each little, like this, yeah. So z, let's say zi and zi plus 1. All right. I guess with my setup, I probably should be labeling this zi minus 1 and zi for direct applicability to my integral. All right. So I want to just focus my attention on that. So what's going on here? You've got a delta x and you've got a delta y, right? So if we look at d gamma dt, that would be what? We could say that's dx dt plus I dy dt, right? If I set gamma equal to x plus iy, thinking of x and y as being the real and imaginary components of the path here. And so let's see here how to say this. The mean value theorem, right? So if we do mean value theorem on the interval t0 to t1, what's it say about dx dt? It says that there exists, let's say, t star, not on t0 to t1, on what to what? Like the z sub I is, so I need to also do a corresponding partitioning of my t's, and this is where choosing t1 as my upper time was a very, very poor choice. So let's change that t1 to like t total, like t sub t for the sake of discussion here, okay? The total time. Right? Because what I'd like to say is that gamma of tj is equal to zj. I want to partition my my parameter domain in the same way as the curve. I want to pick parameters t sub j that they map to the z sub j's that I've picked on the curve.
Could you call it t sub n, or does that not work?
I could call it t sub n, but I don't want there should be no n dependence in the choice of the parameter domain. And n is going to be, we're going to take the limit as n goes to infinity, so I don't want to have an apparent n dependence there. The upper.
N dependence in like indexing the z's. Maybe I'm misunderstanding.
Well, for any choice of n, p2 is always the last one. So like when n is equal to 2, p2 is z2. When n is equal to 5, p2 is z5. In the same way that the total time should correspond to the output of gamma. When we feed it the total time, we should always get p2 as the point, which is in the path. I mean, let me go on. I think it'll clarify here as we go on. So there should be a t sub. Now, instead of, we want to apply the mean value theorem. So what I'm trying to say is that this is gamma of ti rather, and this is gamma of ti minus 1. So I should not be looking at the mean value theorem on the total time duration, but on the little subinterval ti minus 1 to ti, yeah? Like that. I should be looking at that time interval, and there's a, let's say, ti star, an element of this subinterval, yeah? There's got to be some time in there such that what? The mean value theorem says there's some time in there where the average rate of change in x matches the instantaneous rate of change in x. dx dt of ti star is equal to the change in x over the change in t, which in this case is, x sub, what is it, x sub I minus x sub I minus 1 over t sub I minus t sub I minus t sub I minus 1. Yeah. So I can apply the mean value theorem to trade the change in x over change in t for, and I think without getting into trouble, although this is a little bit of a cheat, I think we can make the time increment between the different z's be the same. So we can, just to keep things from getting super complicated, and I think this is a reasonable and not too much of a jumpy step. We can assume that the time increments between the points in interest are equal. Or at least we could, well, anyway.
Is this because we're assuming the function is?
Yeah, well, it's because I'm trying to make this proof less complicated mostly. So, change in t. I want to say that the change in t is the same, you know. So in other words, I'm suggesting that n times the change in t is just going to be equal to the total time minus the initial time. Yeah. It's like we're dividing the time up into equal increments. Well, at least we could do this much. I mean, I guess there's a slight, I mean, you could think about it this way. The original integral is sampling arbitrary sets of endpoints along the curve to set up the integral. And I'm making the argument that if we set up arbitrary endpoints that are at least spaced along equal time increments of a parameterization, that shouldn't change anything, because we're still passing to the limit as n goes to infinity.
Right.
So that's the abuse.
And you can prove that it's the same as long as the curve is smooth, right?
Yeah, I think we could prove the same, but I think proving the same would get us into questions of integration which are deeper than those I wish to cover in this course, unfortunately. I think those might be measure theoretic kind of questions, yeah. And so we can do the same thing, though. We can do the same thing for the y, right? We can pick also, now not necessarily for the same time, right? It might be a different time. You know? Right? Because we don't know for sure that the instantaneous y velocity matches the average rate of change of y at the same time as it happens for x. Right? We don't have that much. We don't know that. But we do know that there exists some time in that subinterval where that is the case. So let me just point out what this means. This means that, so let me collect my thoughts here. You can. I'm worried. Same I.
Like the same value of I, or
Yeah, I want to consider an arbitrary. I'm trying to consider the ith partition to come the same one for both. And so, in summary, what we have is that we can look at our delta zi, which I'm suggesting that denote this right here. This is delta zi, right? We can take delta zi, and we can write it as, of course, delta xi plus I times delta yi, right? And then by the mean value theorem, we can rewrite that as dx dt at ti star plus I dy dt at ti star star, all times delta t. Yeah.
So we have gamma of t sub I is equal to z sub I, right?
Gamma of t sub I is equal to z sub I. Yes, correct.
So does that mean that gamma of t sub n is equal to z sub n?
Gamma of t sub n is equal to z sub n, yes.
So does that mean that t sub n is equal to t sub upper t?
Yes, t sub n is equal to t upper t for all n.
Oh,
Yeah. That's the setup. It's like when we partition, Riemann sum from A to B, x sub n is always equal to b for whatever n you set up. Yeah. Okay, so what is this then? So we've got the limit as n goes to infinity of the sum I equals 1 to n of f of gamma of t sub I, yeah, times what? Before I write it over here, let me simplify this one step further. Well, I can't. I'd love to just say that this is d gamma dt at t sub I. But then t sub I what? I can't put t sub I star. And I can't put t sub I star star. See, it's the, it's the derivative of the path half at that point and half at that point. But this difference gets washed away in the limit is the thing. So this is dx. I was going to try to save myself some writing, but as I think through it, E is no allowed. Ti star star delta t. And then my argument is in the limit as n goes to infinity, right? In the limit as n goes to infinity, you can see that this limit is the same as the following limit. We can just trade the t sub I stars for just t sub I. Which I'm going to write more concretely as just d gamma dt at t sub I times delta t. That, you're right, Sam, I need continuity to do that, because I need to know that the values of dx dt and dy dt are not jumping as we shrink down these subintervals. Like there can't be any kind of like discontinuity in the derivative. Otherwise that would forbid this passage from this limit to that limit. So I am using the continuity of the curve there and its derivative. But once we do that, and I don't think that's a terribly, I mean, intuitively speaking, I think this is a very reasonable step. If you think about what happens to ti and ti star as the time interval, I mean, what are we talking about? We're talking about this time interval, right? Which is getting smushed smaller and smaller and smaller and smaller and smaller as n goes to infinity. And so, just to draw a picture, this is ti minus 1, this is ti, and ti star and ti star star, I don't know where they are. They're somewhere in here, right? So as you squeeze this and that way, they must all become the same thing. And that's why it's legitimate in the limit to replace these ti stars and ti star stars with just t sub I. In so doing, I go from a sum of the x and y derivatives to just the straight up derivative of the path, right? And then this, what is this? This is a Riemann sum for a complex valued thing. You could break this up into the real part and you could rewrite this in terms of like two honest to goodness real Riemann sums. And in so doing, this is nothing more than the integral. What I'm trying to say is we could extend the definition of Riemann sum to complex valued functions, right? So if I had been willing to spend 3 weeks on this as opposed to 2 days, then maybe I would have spent 10 minutes talking about that, but oh well. We are where we are. So we have the integral from t naught to t sub t, in my current lingo, f of gamma of t, that's d gamma dt. And that is my definition 1. And that's why definition 1 and definition 2 are interchangeable. And it's pretty straightforward to get from definition 2 to definition 3 because it's really just multiplying out. I mean, I can get from definition 2 to definition 3. I'll do that right now. So if we write this in terms of u and v, this is u of gamma of t plus I times v of gamma of t. Yeah? And again, d gamma dt is dx dt plus I dy dt. dt. And so when you multiply this stuff out, what you get is u of gamma of t minus v of gamma of t times, oh, curses. I regret starting this, but it's too late. dx dt dt, dx dt minus v of gamma of t at some point you'd think they'd realize I'm not going to give them money. All right, integral t sub 0, t sub, I mean, I'd love to give them money. I just can't. Let's see here, u of gamma of t. So much writing. But I guess it's worthwhile. The point is, all of this, these actually define carefully the integrals over the differential forms. This is precisely what we define to be the integral over the curve of u dx minus v dy. And this over here, I've lost it. I can only half see. I lost an eye. And then, I'm sorry, that was horrible, truly horrible. U dy plus v dx. So there you go, that was my other definition. It really is just a straightforward consequence of the kind of integrals I was sharing with you last time. All right. How much class time? Oh my goodness, I'm so sorry, guys. Why did I spend that much time on that? I think it's good, though. I think it's worthwhile for you to see these things, actually. Okay. So we've got this complex integral. What are its properties? Right? What are the properties of the complex integral? Care to guess? Yeah, what are the properties of the complex integral? I have a vote for integral of the sum is the sum of the integrals. Now, careful. The dz is not optional, it's required. Okay. So you say that's the integral of f dz plus the integral of g dz, yeah? Indeed, you are correct. How about this? If I have a constant, I'll call it b times f. Can we pull the constant out? Indeed, yeah. Here's a neat thing, though. For the complex integral, if we have f times g dz, we have the integral of f dz times the integral of g dz. That is a lie. It's also not true here. This is just totally nonsense. It's not even true. That's not true. You're so excited, yeah. No. But pretty much, actually, everything else is still going to be the same in terms of just basic algebra of the integral, right? So, yeah, linearity. Let's see here. What else can I tell you at this level? Now, there is one important thing. The integral of a curve of f of dz, f dz is equal to the minus the integral along the disorientation of the curve. I'm sorry, we usually call that the reversal. So if you take the curve and you reverse it, that introduces a minus sign. So the complex integral, or this is also known as the contour integral sometimes. It's much like a line integral, right? And you can explicitly see that in this definition, right? It's actually a complex linear combination of two honest-to-goodness real line integrals, right? I mean, this is the work of the vector field u comma minus v, and this is the work of the vector field v comma u. It's the complex linear combination of those two works. What does that mean physically? I have no earthly idea. What does it mean geometrically? I also don't know. Students always ask this, like, what does it mean, though? Like, what's its geometric meaning? Well, that's probably the wrong question to ask. There are many meanings to this integral, but a direct geometric one, I'm not aware of. And I've thought about it a lot. All right, anyway, I'm not saying you can't figure something out. Maybe you can, but that's that. Now, there's another result which is that if we have that the value of the function is bounded by m for z in the curve, and if the length of the curve is L sub c, denotes the length of the curve, then the modulus of the integral along the curve is less than or equal to the bound for the function times the length of the curve. Also, we make a definition that if we want to integrate like a complex function with respect to arc length, so here, suppose f is complex value, but you want to integrate it with respect to arc length. So if you had some like concept of complex mass density, this would calculate the complex mass along the curve S, right? Or perhaps you could talk about it being like some sort of active circuit element in an AC circuit, and doing this line integral would calculate its, if it was it could be the density of impedance, and this integral would be the net impedance of the circuit element that's laid out along the curve C or something like that. Impedance is actually a real complex value, real in the sense of, well, you know. Anyway, this we also denote by this. So here's a nice notation. The note, see like the magnitude of dz? What should the magnitude of dz mean? So like dz is dx plus I dy, if you want to think about it heuristically. And so when I think about the modulus of dz, you can think of it in some sense as like the square root of dx squared plus dy squared, right? Which is a good heuristic for ds. How would you actually calculate this? How would this actually be calculated? Specifically, this would be the integral from, say, t naught to t sub t of f of gamma of t times the modulus of d gamma dt. So you take the magnitude of the velocity, which is the speed, and integrate it against f over time as appropriate. The other thing I've been hiding from you guys is we also define the complex integral along things which are not just plain Jane smooth curves. Like we can talk about complex line integrals along piecewise smooth curves. How do we do that? Often these are called an arc. An arc is a union of piecewise smooth curves. So how would you define the integral along something like this? So here's a horrible example. C is the union. I guess in a more civilized notation, I could say I equals 1 to 8 of C sub I. It's the union of these curves. And that union is not just a set theoretic union. I'm actually thinking of them as being ordered, right? Something is lost in the notation, but I'm thinking of these curves as being one after the other. That's important because the integral is sensitive to reversals of curves, right? So if I did these out of order, well, I guess if actually it wouldn't matter if I did them one before the other as long as I kept the orientation of each one the same. That is true. Anyway, definition. The integral along C of f dz is equal to the sum I equals 1, in my current context, 8. I put an infinity there. Sorry, I multiplied my 8 by I, right? If you take I times 8, it's equal to infinity because this is a rotation by 90 degrees, right? Okay, so sorry about that. That's an old math joke. Let's see here. This is the appropriate context for that joke, though. Let's see here. do that joke in calculus, you just get crickets, you know. Let's see here. So c sub I f of z dz. So this is how we actually integrate over arcs. All right. Okay. Let me show you some deeper things. Yeah. What's that? It's a joke. No, it's a joke. I mean, I times a complex number rotates it by 90 degrees, right? So if you so if you take 8.
But were you trying to notate IDD and when you rotate?
So this is a joke.
No, at the. Oh.
Oh, okay.
That's actually number 8.
Yeah. I mean, generally speaking, if it's an arc, we can write it as a joining of n smooth curves, right? So this would generally be replaced with like the union of n smooth curves, and we just take the sum I equals 1 to n like that, and that's how we do it. Yeah, I don't know about that. That's outside my domain. Listen, one of the things we ought to do before I get the projector out is to do this one. What's the integral of z to the n dz along the curve c sub r? And let's let c sub r be the clockwise oriented, r e to the it such that 0 less than or equal to t less than or equal to 2 pi. In other words, it's just a counterclockwise circle of radius r. So let's calculate the integral of z to the n dz. What's this equal to? So integral from 0 to 2 pi, yeah? And then we've got r e to the it raised to the n power. And what's the definition? I mean, I was kind of nice to you guys. I gave you gamma of t. It's right here, yeah? So what's d gamma dt? D gamma dt is I r e to the it, yeah? These shoes, the funny thing about these shoes is they like suction cups, and they're like pop, but I can't make it happen. It just happens. Cool. Yeah. I hit the edge, and then it bounced off the wall and in. It was like a, yeah. All right, and then, oh yeah, we spent a lot of time working this out. So f of gamma of t, right? Which is the raising it to the n power, then the gamma dt, which is IR to dt, and then dt. All right, so what's that? Looks like we've got r to the n plus 1, integral from 0 to 2 pi, e to the n plus 1 it dt. So that integral is r to the n plus 1 over I times n plus 1 e to the n plus 1 it evaluated from 0 to 2 pi, which is what? I'll bring the I upstairs just to be annoying. Doesn't matter. What we got? We've got e to the 2 pi times n plus 1 I minus e to the 0. What is that equal to? What's that? Say again? Get rid of the 2 pi. Yeah, what is e to the, well, 2 pi times n plus 1 is a integer multiple of 2 pi. What's e to the integer multiple of 2 pi times I equal to? It's 1. 0. We have 0. Right? So what I'm saying, this is a little bit shocking, is that if you look at f of z equals to z to the n, right? This corresponds to p plus iq, right? Well, excuse me. Well, yeah, p plus iq. How did I say this before? Well, remember we worked out last time how to say this. I don't want to say more than that. I'm sorry. Let me shut up. I don't need to say that right now. This is 0. Now there is a exceptional case. Yes. What's the 1n that my calculation does not make sense for? Yeah, 1. It's the 1. So n equals to, well, not 1, but yeah, negative 1. N equals to minus 1, this does not work, right? What happens in the case n equals minus 1? So there, we've got r e to the it to the minus 1 power, yeah? Times I r e to the it dt. Integrate from 0 to 2 pi, what happens? The r's cancel, right? Because that's 1 over r times r. And then we get e to the it, well, e to the minus it times e to the it. And there's an I, right? That I. So there you go. 2 pi I. So let me put it into some lingo for you here. Well, let's say it this way. Certainly, omega equals to dz over z is not an exact form on a region which includes the circle of radius r. Because we've just showed that the integral around that loop is non-zero, which says that that differential form is not exact. On the other hand, z to the n dz might be an exact form. At least the integral around this one loop is 0. To show that z to the n dz is an exact form, I would have to do what? D of what? Apparently whatever I'm about to write down there does not make sense for n equals to minus 1. Right? But you guys can do it. It's 1 over n plus 1, z to the n plus 1, yeah? That is the potential form for z to the n dz. It's exact, that's its differential. I mean, it's the differential of that function. When you differentiate that, you get n plus 1 times z to the n plus 1 minus 1, which is just z to the n dz, taking the differential. Now, how about this one? If I tried to write omega as the differential of something, what would that something be? In other words, I'm asking omega is equal to f prime of z dz for what f? What f? What f would I put there? I guess I should use h using my notation from the other day, yeah? Use infinity. The natural log, I take your log and I make it unnatural. So yes, log z. Log z will do. But, in fact, any branch of the logarithm would do. But what's the trouble? I mean, that doesn't include the circle, right? There's no contradiction there. See, because the log is not holomorphic on all the way around. It's got that angle jump somewhere. And so there's no contradiction in finding this non-zero integral because so let me describe the situation here. In fact, we could define log of z. An alternate definition for log z is the integral from 1 to z of well, I probably should not use z up here. I'd probably say dw over w. And that, so if you make this, we start at 1, we go to z along some curve. I'm saying that the that integration is actually independent of path. We can show that. So if you took calculus 1 with Dr. Sprano, he probably defined the log as what? The natural log. You may remember natural log. So you can use this to define the natural log, I believe.
So you just have to choose what ray to exclude from the domains of these groups. And then that gives you different logarithms.
Yeah. Yeah. But I think they are all generated from, well, you can't always generate them from 1. If the ray you're excluding is the positive real axis, then 1 is not a good base point for this integration. But well, I have so many neat things I was going to show you today. The proof, I should mention this at least, the proof that theorem I erased and had up there, the Ml theorem, it's called, well, I usually call it the Ml theorem. And that is proved well, it's proved on page 128, and it's actually very simple to prove it on the basis of, in fact, really, honestly, guys, the only reason I'm talking about this definition is so that I can write down this very simple proof of the Ml theorem. That's pretty much the only use I have for this definition, is that it allows such a beautiful and simple proof of the Ml theorem, which happens to be near and dear to me because it generalizes to acalculus. The other proof of the Ml theorem involves this very sneaky, tricky thing with polar coordinates, which is only good for complex analysis. So, and I have the sneaky only complex proof also on page 128. So we'll pick up next time with section 9.2, where I will talk about the fundamental theorem of calculus for complex functions, and then we'll go on to prove Cauchy's theorem, and hopefully Morera's theorem, maybe Gorsaw's theorem next time. I will use the projector next time. There's no earthly way I can get through these proofs in a reasonable amount of time otherwise. So, thanks.